Our results are almost the same, so. Should I begin? So I'm going to talk about our work on the fully dynamic maximal independent set problem. It's a joint work with Soheil, Behnezhad, MohammadTaghi, Hajiaghayi, Stein, and Madhu, Sudan. So independent set of a graph is a subset of its vertices where no two of them are adjacent. For example, here I have two different independent sets of this graph. And maximal independent set is an independent set that is not a subset of any other independent set. So for example, the left one is MIS, or maximal independent set, but the right one is not. MIS is considered as one of the fundamental problems in theoretical computer science, as it has countless applications in both theory and practice, such as approximating matching and vertex cover, graph coloring, clustering, and many other problems. Let me explain our problem formally. We have a fully dynamic graph G that undergoes both edge insertion and deletion, and our goal is to maintain a maximal independent set of this graph that with a small update time after each edge update. Let's assume that this is our graph at some point in the algorithm, and the red vertices are the MIS that we've maintained so far, and we have this edge inserted. We have to remove one of its endpoints from the MIS, because now they're adjacent. Say I remove this vertex. Now I have an independent set, but it's not maximal. So I add these three vertices and make it an MIS. Now let's see how edge deletion works. If I delete this edge, nothing changes in my MIS. But if I delete this one, I deleted this one, and I have to add a vertex to make it MIS. OK, so this problem has been extensively studied during the past years. The first work to consider it was in Part C 2016 by et al. And they give the first algorithm with update time of delta, where delta is the max degree of the graph. And the first one to break the O of M barrier is by Asadi et al., which they give an update time of O of M to the power of 3/4. Oh, let me explain why O of M is very simple. After each update time, we can just construct the MIS from the scratch with a simple greedy algorithm, which takes O of M. And so after other series of work, still the state of the art before our work was polynomial. But in this work, we give a polylogarithmic algorithm. We give an algorithm with polylogarithmic update time. And as you know, there's an independent work by Chechik and Zhang, which has almost the same result. And he will present it. So here is a summary of our results. For MIS, we designed this data structure that maintains a random order lexicographically first MIS. It's a specific type of MIS. I'll explain what it is later. Against an oblivious adversary in a fully dynamic graph that per update takes polylogarithmic time in expectation, and the number of adjustments to the MIS is O of 1 in expectation. We also show that our similar ideas work for maximal matching, and we get the same results for that. But for maximal matching, already efficient algorithms exist, but ours is interesting as it maintains random order lexicographically first MIS, which is by itself interesting. Okay. Here are also two implications of our work. First is a tree approximation of correlation clustering. And the second is that we can modify our algorithm to get a polylogarithmic time worst case update time with high probability. Sorry. I'll just give a very brief overview of our work because I don't have time. So as I said, we'll maintain a lexicographically first MIS, not an arbitrary MIS. And this idea is used by others before as well. So what is a lexicographically first MIS? I'll explain an algorithm that constructs it, and this is the way. So we first say that all the vertices are alive. Then iteratively, we take the alive vertex with the minimum rank. Okay, as I said, ranks are random. And here the number on each vertex is its rank. So the first vertex to join the MIS will be 1. Then after this vertex is joined the MIS, we kill all its neighbors and itself. Then we repeat this. 3 will be joined, which has the minimum rank amongst the remaining, kills the neighbors. 5 joins, and 7. Now one might think that, okay, maintaining this lexicographically first MIS might make your life even harder. And I'll show you that in how it's different from MIS. If I insert this edge, I have to remove 3 from MIS because it has higher rank than 1. If I wanted to just have an arbitrary MIS, I was done here because it's already an MIS. But because I want to have a lexicographically first, I have to add 4 because it doesn't have any neighbor of lower rank in the MIS. Because of that, I'd have to remove 5, add 6, and I'm done here. So it seems that lexicographically first MIS should be harder to preserve than MIS. But it has this interesting property that's shown by Century et al. That for a random permutation of vertices, the expected alteration to the MIS after edge insertion or deletion is O of 1. Despite having this observation, the update time given in this paper is O of delta, because even knowing that the number of edges, the number of vertices that will be changed are O of 1, you still need to find them, and detecting them is the way that they detect them is that they go over all the neighbors of altered vertices. So we need to break this. To overcome this issue, we start by defining an eliminator for each vertex, which is the vertex that kills this vertex in the LFMIS algorithm that I mentioned. How does that work? Here, for example, when I add 1 to the MIS, it will be the eliminator of itself, 2, and 8. 3 will be the eliminator of itself, 4 and 6, and 5 is only its own eliminator. So we have this observation about eliminators that makes them very useful, is that changes in the MIS status of a vertex will not affect other vertices whose eliminator has lower rank than this vertex. Let me show you, for example, if I add this edge here, it will not change 8 because its eliminator is 1 and it has lower rank than all the other vertices that are changing. So our idea here is to maintain not only the LFMIS, but also the eliminator of the vertices. So I'll just give you a very small thing about our analysis. We have these 2 results. The first is that we show that for any arbitrary vertex addition or deletion to the expected number of vertices whose eliminator changes is O of log n. So this means that the number of vertices eliminator changes is limited. But we also need to show that for any of these vertices, we don't change our graph significantly. So we show that we can add some other components to our data structure, and in a way that we can update it in polylog n per affected vertex. Affected vertex is a vertex with eliminator changes. But this will not still give us the desired update time, because our expected update time is equal to the expected number of affected vertices time updated time for each vertex. But these two are not independent. Number of affected vertices is not independent of the update time for each vertex. If they were independent, we would have our result now. But for analyzing this, we need to be more careful, and we have the results in our paper. We can take it offline if you had any questions. Now I have to give it to. Thank you.
We have time for 1 or 2 questions before the second part. While the second part of the.
Okay, I'm sorry. Okay. We are going to take the question. Okay. Any questions?